I chose this topic, extraterrestrial intelligence, because I thought it would be particularly interesting for skeptics, because it combines both necessity to have imagination with critical thinking. You have to imagine big things, but also then filter down what is possible or weight what is likely to be true with critical thinking. I just want to put this little plug in here. I'm a programmer. I'm not an astronomer, I'm a programmer. I have an interest in astronomy, and I wrote this application called Planets for the iPhone. And I had my 15 minutes of fame on April 1st when my picture appeared in the Ottawa Citizen. Feel free to download it. It's for free. Just search for Planets. It's for the iPhone, iPod Touch, and iPad now. Okay, the first thing I wanted to mention, skeptics you probably are familiar with this. Some claim that aliens are already here. And the 2001 Gallup poll said the US population found that about 1/3 of people believed that the Earth had been visited by aliens sometime in the past. And there's a whole host of different claims that people make about aliens already being here. I won't bother going through them. The bottom line in this is that there's insufficient evidence to conclude that any of this is actually happening. What we've got is eyewitness testimony, anecdotal reports, people seeing UFOs and such. In the court of law, that's eyewitness testimony is thought to be very reliable, but in the court of science, eyewitness testimony is probably the lowest form of evidence one can have. What we need would be some sort of artifact, some sort of technological or biological artifact that would be undeniably of alien origin. That would be sufficient evidence. If you're abducted by aliens, as they're doing those rude experiments on you, please grab something off the shelf and put it in your pocket, because we'll need that sort of evidence to prove that aliens are visiting us. And this is another thing from popular culture. People say, oh, UFOs, a UFO is an alien spacecraft. They've forgotten the actual definition. UFO is really an unidentified flying object. So what this is really is an argument from ignorance. It's saying, unless you can tell me what that object is, you must accept my claim that it's an alien spacecraft. We also hear this kind of argument, if you can't tell me exactly how the pyramids were constructed, then you must accept my claim that the pyramids were constructed by aliens. That's not really logically sound. And the other kind of thing we often hear is conspiracy theories. Evidence exists, but it's being suppressed by the government. Unfortunately, that's sort of a dog ate my homework approach. Saying that good evidence exists, but it's being suppressed, it's, we have to have the evidence. We can't have an excuse for why there's no evidence. Unfortunately, this sort of taints the search for extraterrestrial life scientifically, because people associate these sort of wacky claims with the scientific search for extraterrestrials. And that's unfortunate, because it means that governments are less likely to fund the SETI because of this association. Oh, and by the way, this also means that people kind of go the opposite extreme. They say, well, because there's no evidence that aliens are visiting us, therefore there are no aliens. It's the opposite extreme. Of course, they're totally ignoring the middle ground. Aliens could exist, but just aren't visiting us, right? That's the by far the most likely scenario, I would say. So what is the evidence for extraterrestrials? The simple truth is we actually don't have any. There's no evidence at all that there is any life beyond Earth. Now, there's some really tantalizing things that we've seen, like a meteorite that has definitely come from Mars. We analyze the meteorite, and we find that its composition is from Mars. And some say that the meteorite actually has evidence of microbial life, but that's very controversial. Really, it hasn't been unambiguously determined that that is an artifact of alien life. Now, we might find alien life within our solar system. There's moon Europa that orbits Jupiter, and it has a lot of water. Europa is basically a water world. If we're able to send a probe there, we might actually find life within that Europa seas. But we haven't yet. Okay, so here's the main question. Are they out there? The position that intelligent alien life exists, but somewhere else, is quite plausible. For example, here, this picture you see here is a Hubble Deep Field image, and every single little smudge on that image is another galaxy. If you do this across the entire sky and count them up, you get about 10 to 11 galaxies, so that's 100 billion galaxies. And each of those galaxies contains about the same number of stars, 100 billion stars in each galaxy. The Milky Way maybe is a little bit larger. It has maybe around 300 million stars in it. So you do the math, multiply them together, you get 10 to the 22 stars. Well, that's enormous. That's an astronomical number of stars, literally. To claim that only one star has intelligent life around it seems like an audacious claim, saying there's exactly one star that has intelligent life. We assume, with no evidence, that most likely there's intelligent alien life. Now the problem, though, is that this same huge scale, although it probably makes life very certain to exist, it also potentially prohibits us from ever interacting with those aliens. Now, just to throw out a few more numbers, the universe is approximately 14 billion years old. The Earth is about 1/3 of that, 4.5 billion years. And us humans, the modern versions of us humans, 200,000 years. So we're newcomers. Oh yes, by the way, I should mention 10 to the 22 stars, that's the visible universe. The actual universe is a little bit larger than the visible universe. Potentially much, much larger than the visible universe. I just want to mention a few heroes of SETI. SETI standing for Search for Extraterrestrial Intelligence. The first one being Carl Sagan. He's probably the most well-known skeptic there ever was. He published many books. Here's one of them, The Demon-Haunted World. An excellent read. I highly recommend this. One of the quotes from this book is, "For me, it is far better to grasp the universe as it really is than to persist in delusion, however satisfying and reassuring." That's, I think, one of the core tenets of skepticism. The other person I wanted to highlight is Frank Drake. This man's about 80 years old now. He's still alive. He's still active. Frank Drake is probably best known for this equation that he wrote. The Drake equation is a way of estimating how many technological civilizations are in our galaxy right now. It breaks it down into all these factors. They're all multiplied together. The first factor is the rate of star formation in the galaxy. Now, this is a number we know well. It's about 10 stars a year. So within our galaxy, there's 10 new stars every year. Now, these next three terms is something we don't know, but we can determine using scientific inquiry. The first one is the fraction of stars that have planets. The second one is, of those, the fraction of habitable planets. And the third one is the fraction of those on which life arises. So those things we can actually address scientifically. And I'll go into how we can address those scientifically. Now the last three, unfortunately, are more speculative. We have to speculate in order to get these numbers, and that means that the n ultimately is a speculative number. First one of these, the fraction of planets on which life arises, the fraction of those that develop intelligent life. The second one is, of those, the fraction that develop a technological civilization. And the last one is the average lifetime of technological civilizations. Unfortunately, since we only have the Earth to look at, sample size 1, where it's going to be very difficult to get a handle on these last three variables. By the way, if you ask Frank Drake what his estimate for n is, it's about 10,000. Yes?
Just a question, why is technology relevant?
Oh, the reason why is because these are the civilizations which we can communicate with. If they don't have technology, basically we have no way of communicating with them, we can't interact with them. So yeah, by this definition, an intelligent civilization is civilizations that can build radio transmitters. Humans have only been intelligent by this measure for 100 years. The first radio transmitters are 100 years old. Marconi in 1897 built the first transmitter. So anyways, Frank Drake, his guess was 10,000, but his guess is no more valid or less valid than any other person's. So how can we get a handle on these variables in the Drake equation that are things that we can know? Well, in the last 2 decades, we've really made a lot of progress here because we've discovered exoplanets. Exoplanets are extrasolar planets. They're planets outside our solar system. In 1988, we discovered the first exoplanet, and since then, there's been 452 planets discovered. And they've discovered with 5 different techniques. The most straightforward one is direct imaging. That's where you point a telescope up and you see the planet. The problem is that the star is so incredibly bright compared to the planet, so it's very difficult to see the planet, unless it's very far away from the star, in which case it's probably not conducive for life because the planet has to be so far away from the star. So direct imaging is only been used for a handful of exoplanets. The most popular ways of detecting stars are, one of them is called Doppler, and basically what happens is when a planet orbits a star, it causes the star to wobble. So you can see the planet going around the star, and the star basically orbit their common center of mass, the barycenter. So we don't see the planet, but we see the star wobbling. It's moving very slightly, so the way that we detect it, when the star wobbles, it actually comes toward the Earth slightly and away from the Earth slightly. And when it's going back and forth like this, there's a Doppler effect. What happens when an ambulance with a siren on passes you by, you hear a drop in pitch. Same thing happens to the light. It becomes bluer and redder as a result of the star coming toward us and away from us. So we see the variation in color. And with this, you can actually estimate how big the planet is and how far away it is from the star. The bad news here is that we can only really detect Jupiter-sized planets with this technique. The Earth produces too small a variation in the star for us to detect. So it's not very good for detecting Earth-sized planets, but we found lots of Jupiter-sized planets, especially ones that are really close to the star. The Jupiter that's very close to the star is really unlikely to have any sort of life. We're really looking for terrestrial planets because we know they can support life. And the second technique is this thing called transit. The solar system we're looking at has to be oriented to us such that the planet passes in front of the star. When it passes in front, it causes a slight dip in the brightness from the star because it's obscuring part of the star. And this is a pretty sensitive technique because you can actually detect Earth-sized planets. And what has to happen, though, is you have to actually see maybe 3 dips in a row, and the dips have to be nicely evenly spaced, and then you can say, oh, that's probably a planet doing that. But this, like I say, can detect Earth-sized planets. Problem is that it have to be edge-on, and these things are normally randomly oriented. So you have to view a large number of stars, and hopefully some of them are randomly oriented to allow for this technique. Now, one other great thing about the transit method is that if that planet has an atmosphere, the light from the star may pass through the atmosphere of the planet on our way to Earth. We're getting some sunlight that's been filtered by the planet's atmosphere, which is great because then we can break that down into a spectrum and we can look for spectral lines. And these are what's called absorption lines. They are characteristic of the elements that are in the atmosphere of the planet. And so we can actually get a reading of what's in the planet's atmosphere. Such an incredible distance away, we can tell what's in the planet's atmosphere. So if a planet's got methane or oxygen or ozone, then that's a sign that there might be life on that planet. Actually, we're going to get a lot more planets discovered very soon because this mission, the Kepler mission, it's a satellite that was put up in March 2009, and it's on a mission that's going to last 3.5 years. And what it's doing is it's staring at a part of the sky near Cygnus, the constellation Cygnus, and there's about 145,000 stars in its field of view. And it's just staring at those stars, looking for transits, recording the brightness and looking for transits. It's got to look for about 4 years because it's looking, it has to see the dips several times in a row. But we're going to be discovering Earth-like planets in the next 4 years. Kepler, by the way, is looking at a patch of our own Milky Way galaxy that's about 3,000 light years away. So that's the area of the Milky Way that is being surveyed right now. Great news for detecting planets, determining how many planets there might be out there and whether or not they've got the right kind of atmosphere for life. Okay, but what about another approach? What about just simply detecting aliens directly? This is the movie Contact from 1997, based on a book by Carl Sagan from 1985. And by the way, unfortunately, Sagan died during the filming of this movie. He died December 1996. Very unfortunate. There's a couple things here you notice. It's Hollywoodism. Jodie Foster is standing in front of the VLA, the Very Large Array in New Mexico that was never used for SETI. Also, she's listening with headphones. That's really unlikely for a SETI researcher to do, right? They need huge banks of computers instead to detect the signal, not listening on headphones. But besides, it makes for a good Hollywood story. Now here's how SETI's actually accomplished. Here's the Arecibo Radio Observatory in Puerto Rico, built in 1963 under the direction of Frank Drake. And it's about 300 meters across. Interestingly, the funding for SETI, unfortunately, was cut. It used to be funded by NASA. Now it's been funded only privately for the past few decades. And all the computer time for processing the data is actually donated by people like us. I've been running the SETI at home screensaver for the last decade, and what it does is it just downloads a chunk of radio telescope data from Arecibo, does processing on it, try to detect a signal of some sort, and then upload the results back to Arecibo. And then so they aggregate all this, and basically right now there's about 250,000 computers involved with SETI at home, and it actually it constitutes about 1/3 of the fastest supercomputer now. It's equivalent to what the computer time that people are donating using SETI at home. So if you go to setiathome.com if you want to have your computer do something more useful than draw pretty graphics when you're not there. They're actually moving over to this Allen telescope array. So this is going into service right now. And it's called the Allen Telescope Array because there's a $30 million donation by Microsoft founder Paul Allen. It's got 42 antennas now. It's going to have 350 antennas. And it's about 500 kilometers from San Francisco. So this is going to be the next wave of SETI. Now let's flip this thing around, right? We're talking about detecting aliens. Of course, we haven't detected any signals yet. We would have heard about it if these guys had detected a signal. Let's turn it around and say, well, could the aliens detect us instead? Is that possible? Here's the Milky Way galaxy. Here's Earth in the Milky Way. And by the way, Milky Way galaxy about 100,000 light years across. That means the light beam takes 100,000 years to cross it. We've been radiating signals for the last 100 years. Now, I was going to draw a little circle around Earth here to indicate how much of the Milky Way our signals have reached. Unfortunately, that circle would be less than 1 pixel, so I couldn't draw the circle. Now, this is partly why it's so unlikely that we'd be being visited by aliens because, well, they don't know we're here. How could they know we're here? We haven't radiated signals out for them to be able to detect us. It is true, though, that in the last 100 years, our signals have reached certain nearby stars. Within 50 light years of the Earth, there's about 2,000 stars. And here's a diagram that's showing about 133 of the brightest ones, which we can see with the naked eye. Now, does anyone know, by the way, does anyone know what the closest star to the Earth is? Dave?
Centauri, Alpha Centauri.
Alpha Centauri. Good guess. You know what? The answer is the Sun. The Sun is the closest star.
Yeah.
Okay, it's a quick question.
That was close.
Okay, so except the Sun is 8 light minutes away. The closest star besides the Sun is Proxima Centauri. It's 4 light years away. So now here's a question. Supposing there was an alien civilization around the Proxima Centauri system, and they had an antenna like Arecibo pointed at us, could they detect the Earth? And the answer is, unfortunately, no. They couldn't detect the Earth because our transmissions, our radio and television transmissions are actually too weak to be detected, even from the nearest star. They might actually be able to detect Earth because they might be able to see the military radar. Military radar is actually pretty strong, so they might be able to detect the military radar. That's the problem with these leakage signals. They're actually pretty weak because they're going out in all directions. They're very weak. If you actually beamed a signal, like if we transmit a signal from Arecibo toward Proxima Centauri, no problem then. You could actually see that signal a couple hundred light years away, in fact, with equivalent type of hardware on the other end. But the problem with beaming signals is, of course, with 100 billion stars, where do you point your radio telescope to transmit? There's a problem there. Either you have to expend a huge amount of energy broadcasting signals in all directions, or you have a focused beam toward one particular location. Now, this actually has been done. We have beamed signals out to particular locations. This was done in 1974 by Frank Drake. He actually turned on the transmitter of Arecibo. You can use it for transmission as well as for reception. Well, the problem, though, is like, what do you transmit, right? How do you speak to aliens? Frank Drake and Carl Sagan came up with this message. It doesn't look very understandable just from glancing at it, but we hope that aliens would actually spend some time trying to decode it. And so here's the type of message they hooked up. The first part of it is just the binary numbers 1 through 10. The second part is the elements of the DNA atom. The next one is the sequence of DNA nucleotides. And then a diagram showing what a DNA double helix looks like. And then a really crude symbol showing a human in the middle. Very crude. On the left-hand side, there's a binary number that indicates the average height of a man. On the right is the population of the Earth in 1974, which was 4.2 billion in binary. The next part is the planets of the solar system. There was 9 back then. And notice the third planet is highlighted, so that's the special planet. And the next part is, here's a diagram of the radio transmitter, the Arecibo radio transmitter, and a number that indicates the diameter of the transmitter. So that's the message that Frank Drake and Carl Sagan decided to transmit for 3 minutes toward the M13 cluster. And by the way, it's very unlikely there would be any life in the M13 cluster. There's not enough heavy elements in M13. This is mostly just a gesture. It's not a real serious intent at communication. Plus, it only lasted for 3 minutes. But that raises the question, should we be broadcasting our existence to aliens? There was a series, you might have seen it, Stephen Hawking has a series called Into the Universe. And one of his episodes, he says this: if aliens ever visit us, I think the outcome would be much as when Christopher Columbus first landed in America, which didn't turn out very well for the Native Americans. Which is true, but I respectfully disagree with Stephen Hawking in that I think this is a false analogy. The Earth is very finite. There's only a limited amount of resource here. It's only natural that cultures on the Earth are going to come into conflict over resources. Imagine if the Europeans sailed to North America and they didn't have one new world, but they had 5. And only one of them was occupied by an indigenous population. I'm sure they wouldn't pick that one, right? That would be trouble. That's unnecessary trouble. They would pick one of the unoccupied ones. Same thing for intelligent aliens. There's no reason for them to select Earth. There's a lot of real estate. They don't have to be selecting us. And plus the fact that it takes vast resources to cross interstellar space. To use up those resources to get resources just doesn't make any sense, right? It just Stephen Hawking must have watched Avatar before he made this series.
I think what he was going on about was aliens who were nomadic. So they wouldn't have to take the resources anywhere. They could go there, use them, move on.
Right, I see.
Like
yeah.
Independence Day.
Right, okay, good point. Good. So hopefully they would be selecting something other than the Earth, because there's too much trouble with the natives here. They'd pick some other unoccupied planet instead of the Earth, hopefully. Because there's just a lot of real estate out there. No sense in trying to take our land. So what about interstellar travel? Of course, this is a sci-fi staple. I want to pull up a quote here that you must be familiar with. Captain, you cannot change the laws of physics. It's kind of ironic that Scotty should say this because sci-fi writers change the laws of physics all the time. In the case of Star Trek and other series, they generally want to break this rule. In 1905, Einstein's theory of relativity said the universe has got a maximum speed limit. It's around 300,000 kilometers per second, the speed of light. The speed of light is constant, but time and space can vary depending on your perspective. There's a lot of implications from this. This is problems because this limits how fast we can travel interstellarly. Maybe we can break that. Maybe we don't understand everything about physics, of course. Maybe we'll find out that that's not true. That might be true, but the problem is that, for example, relativity predicts that if you can go faster than the speed of light, that amounts to going backwards in time. So you could actually, if you can go faster than light, you can actually arrive before you left. You could even try stopping yourself from departing, so there's this great paradox that results if you can go faster than light. If you ask me, I suspect this rule is a hard and fast rule. We're not going to find any sort of way around it. So when we're imagining things, I think it's useful to imagine sci-fi technology. I think, we're going to have sci-fi technology in the future. What we're not going to have is sci-fi physics, because you cannot change the laws of physics, right? I think we have to hold off and not try to imagine or restrict ourselves from imagining a world in which important physical rules are broken. It might be true, but I don't think we should assume it. So that means that if we're trying to communicate, let's say we're communicating with extraterrestrials, Cairo 7 is a Earth-like world that was discovered in February last year. Well, Earth-like, it's Earth about the same size as Earth, but it's very close to the parent star, so it's unlikely to have any life. But just imagine that tomorrow Arecibo receives a signal, and we realize that it's coming from Cairo 7, 500 light years away. And we crank up the transmitter on Arecibo and send back a message. And then, of course, they receive it 500 years later and send back a response. Well, we get our response in the year 3010. it's really slow conversation. So this is the problem with trying to communicate with extraterrestrials. Even when they're in our backyard, we got a 1,000-year lag here in our conversation. So that's a problem. So if sending signals takes such a long time, what about traveling there instead? Well, this would seem to be even harder, right? Because signals travel at the speed of light, which is the maximum. But there is actually some possibility here. Supposing we have a spacecraft and we're able to accelerate in that spacecraft at 1 g continuously. 1 g is pretty comfortable, right? It's 9.8 meters per second. It would simulate what we feel here on Earth with the pull of gravity. After about a year, our spacecraft is getting pretty close to the speed of light, just 1 g acceleration. Now, we never exceed the speed of light, of course. It's sort of asymptotically approaching the speed of light. Halfway to our destination. We have to stop accelerating at this point because if we were to continue accelerating, well, we don't want to fly by our destination at light speed. We want to stop when we get to our destination. Halfway to our destination, we turn around, fire the engines in the reverse at 1 g so that we have a comfortable ride again. And by the time we reach our destination, we're stopped. How long will this take? Okay, well, let's pick a different destinations. Let's pick star Vega, 37 light years away, the center of the Milky Way galaxy at 30,000 light years, or our nearest neighboring galaxy, which is Andromeda, at 2 million light years. There's good news and there's bad news. The good news is, actually, from a person on the ship, it doesn't take all that long. To get to Vega, it only takes 7 years. To get to the galactic center, 20 years, and Andromeda takes 28 years. Not bad. Well, it's not really a quick trip, but it's within a human lifetime. But there's some bad news. First bad news is, well, that's from the perspective of the person on the ship. From the perspective of the person on Earth, it takes a lot longer. It takes as long as the distance in light years, right? The ship's traveling near light speed, so Vega takes 37 years, the galactic center 30,000 years, and Andromeda 2 million years. Good luck getting funding to build your spaceship because this is no one's going to be waiting for you at the spaceport when you get back home. Let me put it that way.
Yeah, but think of the amortization period.
That's true. Okay, so that's bad news number one. Bad news number two is it's going to take a bit of fuel. For every kilogram of payload to go to Vega, it'll take 886 kilograms of fuel. And we're not talking like rocket fuel. We're talking matter and antimatter. Combining those, and they annihilate and produce pure energy, like the most dense possible type of fuel. So, even with the densest possible fuel, we got about 1 million tons per kilogram to get to the center of the galaxy, and about 4.2 billion tons per kilogram to get to Andromeda. We're not breaking any laws of physics, but I can't imagine making a rocket that has that much fuel. It just seems totally outside the realm of possibilities, even though we're not breaking the laws of physics. Oh, there's a bad news number 3, by the way. Bad news number 3. The cosmic background radiation gets really Doppler shifted to lethal extremes. In fact, hot enough to melt any shielding of any known material right now. So besides these small technical challenges, we don't break the laws of physics. So it's not very practical, but possible. Let's change over now. Well, where does a planet have to be in order to support life? We want to kind of estimate how likely it is to have life. Each planetary system basically has what's called a habitable zone. Here's where the zone in which liquid water can exist, right? We're just the right distance from the star, such that we're between boiling and freezing. Now, it's true that maybe for life on Earth, everything requires water, liquid water. It's true that we could imagine other types of life that are completely different from life on Earth that don't require water. Maybe they require liquid ammonia or something. But we're getting into very speculative territory. So I think it's better to rein ourselves in and just concentrate on things we know are possible rather than speculating things that might be possible. For stars of different types, of course, the habitable zone changes, right? For the star of the size of the Sun, it's where the Earth is. We're right in the middle of the habitable zone, no surprise. We wouldn't be here if we weren't in the habitable zone. If you get bigger and bigger stars, the habitable zone moves out, but there's a limit because you get a really huge star, it's throwing out lots of ultraviolet radiation, so that's not very good for life as we know it, at least. Not only that, but the really big stars, they live fast, die young. They burn through their fuel in hundreds of millions of years. We need several billion years probably to evolve, right? So a star that only lasts a couple 100 million years, no good. Now actually, we think of our sun as being very typical, but really, it's pretty big as stars go. About 95% of the stars are actually smaller than our sun. So, if there's going to be life, we should be looking at these really small, faint stars because they're very numerous. There's a couple problems though. Like if you can get close enough to the star, you can have a habitable zone. But if you get really close, what happens is the planet can be tidally locked. We're familiar with this in the case of the moon and the Earth. If something is orbiting very closely, like the moon is to us, it gets tidally locked. In other words, the same face of the moon is always facing the Earth because of these forces, the tidal forces. And that same effect can happen for planets that are orbiting the star really closely. They get locked so that the same face of the planet faces the star, which is a problem because then you have perpetual sunlight on one side and it fries, and the other side is perpetual nighttime and it freezes. It's not very good for life. Now there has been some modeling that's been done, and we found that possibly this can allow life to exist if the planet has a thick enough atmosphere to transport the heat from the light side to the dark side. Maybe there's a possibility that life might be there. So this is not an absolute problem, but it does restrict how much livable real estate there might be on the planet. So anyways, this sort of controls how many planets there might be that are habitable. There's another limiting factor too, and that there's actually a galactic habitable zone too. Here's the Milky Way. There's where Earth is. It turns out that if you're too close to the center of your galaxy, there's probably too much radiation there for life. That's not a good place to be live. That's bad real estate for life. Now, no surprise, we're in the habitable zone for our galaxy. Otherwise, we wouldn't be here talking about it. And outside that region, unfortunately, there's probably not enough heavy elements to build planets and people. So that's probably a bad place to be. So there's only a limited real estate in the galaxy for life as well. There's a couple of special things about the Earth that make life possible, and I just want to highlight them. One is our magnetic field. You don't really think about it much, but the sun really produces lots of radiation, a lot of charged particles, high energy charged particles come from the sun, and the Earth's magnetic field protects us from those, right? It basically stops a lot of those charged particles from slamming into our atmosphere. It's protecting our atmosphere and us from these charged particles. And that's created by the iron core of the Earth. The iron core of the Earth, there's convection currents in that iron core, and it causes a dynamo effect. The dynamo produces a magnetic field. And so without this iron core and the convection currents, we wouldn't have our shielding. By the way, the Apollo mission astronauts, when they left Earth and traveled to the moon, they actually left the magnetosphere, and they reported seeing flashes of light, even with their eyes closed. And the reason why is because cosmic rays are hitting their retina, causing flashes of light. And so this is what happens when the universe is a pretty hostile place as soon as you leave the vicinity of Earth. And it's not much of a problem for the moon astronauts because they were out there for 2 weeks, so not so likely to be a problem in 2 weeks' time. But a trip to Mars, which lasts 2.5 years, those astronauts are going to be exposed to a significant amount of radiation. Unfortunately, possibly they'll maybe 50-50 chance that they will have lethal cancer on their return to Earth. That trip to Mars is not as practical as one might think. There's a couple other things too. Our atmosphere, the details of our atmosphere are very important for our life. For one thing, it stops those deadly cosmic rays. They hit the atmosphere and they produce a shower of lighter particles that can reach the Earth. This actually accounts for a good deal of our annual radiation that we're exposed to, which in itself is not necessarily a bad thing, right? Radiation drives evolution. Mutations from radiation cause evolution. So maybe this is a critical thing, letting some radiation through, but not all, or not too much. The atmosphere stops X-rays. It stops most of the really damaging ultraviolet. Some of the ultraviolet gets through, and that's stopped by the ozone layer, of course. So that ozone layer is very critical because ultraviolet light can really has enough energy to break the nucleotides in DNA. We need our ozone layer. Now, visible light gets all the way to the Earth's surface, of course. Some of it's reflected by clouds, and some of it is reflected by the Earth's surface. Of course, a lot of the atmosphere, the light gets through and it heats the Earth. Earth re-radiates that heat as infrared. And now here's another critical thing, right? Some of that infrared gets through the atmosphere out of space. Some of it's reflected back down to the ground, which is a very good thing, by the way, because without that trace amount of gas in our atmosphere, the Earth would be about 40 degrees colder on average. We really want those greenhouse gases, let me tell you. But the problem now, of course, is we're thickening that layer, and that's not a good thing. People think, oh, greenhouse gas bad. Well, no, very good, just not too much of it. Just the right amount. Radio waves come through the atmosphere, which is good for telecommunications and for radio astronomy. Okay, so that's the details of our atmosphere are very important for our life. Another interesting thing is the moon is actually critically important for life. One surprising thing about the moon is it's huge. We have a moon that's about a quarter the size of the Earth, which is a bigger ratio than any other planet in the solar system. We've got a huge moon. And the reason why is because of the way it formed. Back when the Earth was very young, it was hit by a huge planet-sized object, the size of Mars. It threw up all this material into orbit, a huge amount of material, almost shattered the planet. But because of this, we got this massive moon. Well, how could a moon be important for life on Earth? Well, it turns out that the Earth, of course, spins on its axis, and that axis is tilted by a certain amount, 23.5 degrees. And this is what causes the seasons. Fortunately, it's not too severe a tilt, because we'd have very severe seasons if that were the case. But what happens is the moon actually stabilizes this, so that if we had no moon, say, basically what would happen is that axis can actually wander over the course of millions of years. And can you imagine, like, if that axis tilted all the way over, we'd end up with Antarctica in daylight for 6 months of the year, and then the Arctic in daylight, continuous daylight for 6 months of the year. It would play, it'd be hard to imagine what kind of life would survive that kind of extremes in climate. So the moon, fortunately, stops this from happening. The huge moon we have stops this from happening, and we're here as a result. Another really important thing for life is asteroid collisions. And we have this relationship between the size of asteroids and how often they happen. We had an asteroid, a meteor, hit the Pacific Ocean back in 1994, create a big fireball around Micronesia. So that was about a 10-meter asteroid. The largest asteroid in living memory is Tunguska. It's basically a 50-meter asteroid, basically exploded over the air in Tunguska, Siberia, and it flattened about 1,000 kilometers of forest. 65 million years ago was the Chicxulub asteroid, and it destroyed about 85% of all life went extinct when that asteroid hit in the Gulf of Mexico. Now, it sounds like a bad thing, right? But think about it. If that asteroid had been 20 hours early or 20 hours later, it would have missed the Earth completely, and we wouldn't be here. There would be dinosaurs here. This is actually a good thing. No,
maybe we'd be dinosaurs.
Oh, right, exactly. Or maybe the dinosaurs would evolve into intelligent beings. That's true. Good point. Good point. This can really stir things up, and it might be good. Of course, we don't want this to happen again. Now that it's happened once, we want to stop it from happening again. And we might be able to do this too, because with sufficient technology, you can track these asteroids in near Earth orbit and do something about it, like deep impact. There's another interesting thing. The asteroid collision rate is actually strongly influenced by planets in our outer solar system. This is an SKCD comic that's showing the gravity wells produced by different planets. Basically, you can see that Jupiter is a huge gravity well. So if there's an asteroid in some very eccentric orbit, it's likely to either fall into Jupiter's gravity well or get flung out of the solar system completely. So Jupiter actually has really moderated the number of asteroids hitting Earth, because I don't think we want that to happen too frequently. We want it to happen occasionally, but not too frequently. I just want to come back to the Drake equation and the last term here, the average lifetime of a technological civilization. It turns out that this is probably the term that dominates the equation. It's how long do civilizations last? We have to overlap in time with those alien civilizations if we want to communicate with them. Unfortunately, since we have such huge amounts of time, the fact is overlapping in time is a difficult thing unless each civilization lasts an appreciable period of time. And we don't really have a good way of estimating this. All we have is what's happening on Earth right now to decide whether we should be concerned or not. And I guess we do have reason to be concerned because, well, here's a graph of how many nuclear warheads we have and how many megatons that represents. And of course, this is many times more than is necessary to destroy civilization. The fortunate part is that the trend is going down, as you notice. So we are getting rid of these nuclear weapons, but we have to bring it down to a level below the global catastrophe level. So hopefully we can have the political will to bring that down to a really low level. Hopefully alien civilizations, they're going to discover nuclear weapons as soon as they realize E equals mc squared like we did. They're going to have the capability of wreaking their own destruction. Another worrisome trend, of course, is our own population. Since over the last century, it's been going up exponentially. It's more than tripled since 1900. And this can't continue, right? We've got to somehow, hopefully, collectively decide that this trend has got to come to an end. Fortunately, it is leveling off. It's leveling off high, maybe 10 or maybe 9 billion or so. But unfortunately, that means that everyone can enjoy a first world quality of life. But hopefully, this will not cause catastrophe if we manage this. The last one here is the atmospheric CO2. It keeps on going up and up. This is a consequence of our technological society. Hopefully, it's not a common trait amongst technological societies to destroy their own environment. But that's definitely a possibility here. And what the worrying thing here is that people have been investing as much effort in denying the problem as they have in trying to solve it. And that's a very worrisome thing when we deny the problem exists at all. Now there is some saving graces here that might extend the lifetime of our society, of our technological civilization. And one of them is the possibility of machine intelligence. Now here's a trend of how much compute power has changed over time. This is Moore's law, and it's basically the technology has adhered to this trend quite accurately over the past few decades. And if we extend this out to 10 and 20 years into the future, we realize that actually our computers, pretty soon your laptop's going to have as much compute power as you do. So now that doesn't mean it's going to be intelligent. We have to, of course, crack the problem. We have to reverse engineer the human brain. But now at least we'll have the hardware that it can actually implement the intelligence. And so this is a real possibility. We're going to have this way before we have fancy starships that can go travel interstellar distances. We're going to have machine intelligence first. This is kind of a graph you might have seen before. It's sort of satirical, right? It sort of suggests that maybe the height of human civilization was back when we were hunters, and now computer programming somehow is a lowly job. As a computer programmer, I disagree. You can take a serious message from this too, and the serious message is that perhaps technology really is part of evolution. You can think of the development of technology as just a part of evolution. And if you extend this, then you can think of machine intelligence as part of evolution as well. Now, of course, these are Cylons from Battlestar Galactica. So if you believe Battlestar Galactica is usually the future, then this is what you get. Just to highlight this point, evolution basically creates increasingly complex life, and until we get to intelligent animals, which when I say intelligent animals, I mean us, right? But the problem is that with increasing complexity, you get increasing fragility as well, right? We're depending on the ecosystem and everything below us. We're depending on everything below us. So it's sort of like a tower. We're very fragile because we're dependent on so much. But if the next step in evolution is the creation of machine intelligence, the nice thing about machine intelligence is potentially it's not depending on that ecosystem existing forever. And therefore it's less fragile than the rest of life that's been created through natural means in evolution. This is potentially our saving grace. Human intelligence could be preserved in this fashion by having machines be our descendants. So here's my inconvenient truth. To summarize, life might be relatively common, but intelligent life might be exceedingly rare. Our interactions with extraterrestrials will be severely restricted by the vast distances. The longevity of technological societies is a major limiting factor in us interacting with them. And in my opinion, The most likely scenario is our machine descendants meet their machine descendants. So we'll meet, perhaps we will meet, but perhaps it won't be biological organism meets biological organism. Okay, so I just want to finish up here with something that Carl Sagan highlighted back in 1990. Back when the Voyager space probe was leaving the solar system, he asked NASA to turn the camera around on Voyager and take a picture of the inner solar system. And they did that. They produced this picture. Now, you see these colored bands, and that's actually just an optical effect. The camera's pointing close to the sun and getting this scattering of sunlight. So that's what the colored bands are. But you probably can't really see it there, but this little 1 pixel dot there, that's the Earth. Carl Sagan, his point was that we're really like a speck of dust on a speck of dust. We're really insignificant in terms of the cosmos. But we're in charge of this speck of dust. It's up to us to determine what happens. I want to finish up with this quote from Carl Sagan. "We on Earth have just awakened to the great oceans of space and time from which we have emerged. We are the legacy of 15 billion years of cosmic evolution. We have a choice. We can enhance life and come to know the universe that made us, or we can squander our 15 billion year heritage in meaningless self-destruction. What happens in the next second of the next cosmic year depends on what we do, here and now, with our intelligence and our knowledge of the cosmos." Thanks very much.